only take 99% for yourself, and then use the rest for.
You know, there's somebody in the Bible who died because of that.
What? Died from what?
Ananias and Sapphira in Acts.
That he was talking about someone died from the Bible.
Well, we're doing Euler's formula and DeMoivre's theorem. DeMoivre's theorem. And also complex roots. So 3 things. None of them are trivial. No. Let's first do Euler's formula. Widely considered to be one of the most beautiful formulas in mathematics. And we'll learn it if we would be quiet. Euler's formula is that e to the power of I theta is equal to cosine theta plus I sine theta. Now you might be wondering, what in the world does it mean to have a power of I? And that's a good question. That is a good question.
Why is it beautiful?
It's beautiful.
That wasn't an answer. That was a question I got.
You know, you can't explain why something's beautiful, right? You just have to look at it.
I read your
What's the definition of beautiful? Please.
What? I mean, beautiful has a meaning, but once you explain it, it's not beautiful anymore, right? It's like a joke. Okay, so remember last class we learned how to write complex numbers in trigonometric form, right? So if r is the magnitude, then we take r to the outside, and then the inside we can write as cosine theta plus I sine theta, correct? Thank you. That's very helpful when I hear people respond to me. So that means that any complex number can actually be written as r times e to the power of I theta. If you guys take Calculus BC, you'll be able to prove why this formula is true. But if you don't, it'll always be a mystery to you. And that's okay, you know, mysteries are good in life. They keep us on our toes. Anyhow, Euler's formula can be used to derive Euler's identity, which many people love for its beauty, once again. So,
I'm sorry, I was waiting until you paused. And you start talking.
so Euler's identity is e to the I pi equals -1. You might see this on t-shirts sometimes. Well, maybe we have different friend circles. But yeah. I mean, the church I go to is a lot of software engineers, so a lot of nerds. So it's maybe a little different for me. Anyways, e to the I pi equals -1. People really think this is quite beautiful because you combine 3 numbers that seem totally different, right? E, I, and pi. They have no relationship to each other at all, but they can combine to each other and give you -1.
Wow.
Yeah, incredible. Yeah, the hidden structures of mathematics coming together. But anyways, our job today is to solve math problems and not philosophize over this. So, any number can be converted to exponential form from trigonometric form, right? So for example, cosine pi over 6 plus I sine pi over 6, that could just be rewritten as e to the power of I times pi over 6. And we'll see why this is so powerful in question 2, but you guys should do question 1. I'll give you 30 seconds. 15 seconds.
15 seconds.
You just look at it and plug it in, right? Just to get you guys used to the formula, which you guys need to memorize. E to the power of I theta equals cosine theta plus I sine theta. But that's not hard to memorize. Okay, so today we're in the realm of complex exponents. But if you guys do engineering, you'll see this again in your EE classes. And also your quantum mechanics classes if you guys do physics.
Right from Ant-Man?
I don't think Ant-Man has anything to do with quantum mechanics.
Yeah. You actually like shrink people with quantum mechanics?
No.
Are you sure?
Yes. Okay, hopefully you finished question 1. Okay, so 1a is e to the power of I times pi over 3. 1b is 3 times e to the power of I times 5 pi over 6. So, okay, so we're just rewriting trigonometric form into exponential form. And it seems like just a stupid way of rewriting it, but actually it's quite powerful. Oh, do question 2 too. It's not hard. So question 2, you can do the reverse as well. Exponential to trigonometric. Okay, I'll give you guys 2b.
No, it's it'll be like this.
Is this how I do 1B?
Yeah.
That's correct.
Yeah, no, you're right.
Any questions?
So, I don't get how to do this because, like, in questions like this, 3 would be before the b, right?
Yes.
So, can you explain to me how to do this?
You do the reverse of the formula.
Okay, but I don't get how
This
you
is
got 2i.
I. This is I times 2 pi over 3.
I times. Is it like 2? I have no idea.
Am I correct?
Yeah, that's good. Okay, any questions? Let's continue. Okay, where Euler's formula really shines is when it comes to multiplying, dividing complex numbers. Multiplying or dividing complex. Just assume you can read this. I don't know if you guys have seen like the photos of Russian cursive. It's actually much harder to read than American cursive. Yeah. Anyhow, suppose we had 2 different complex numbers written in trigonometric form. So suppose we had z1 equals cosine 2 pi over 3 plus I sine 2 pi over 3. So that's our first complex number written in trigonometric form. And then suppose we had our second complex number, z2, which is equal to cosine pi over 3 plus I sine pi over 3. Okay, and let's say your question asks you to find z1 times z2. This was on your homework, right? Okay, so you could do it the way that we learned last class, which is to convert it into standard form. And then you would get, negative root 3 over 2 plus, don't write this down because it's what you do on the homework. Sorry, that was foolish of me. Negative half plus root 3 over 2 I times 1/2 plus root 3 over 2i. You could do all that and then expand it and then blah, 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 blah. But we're not going to do that because that takes too long, right? Instead, we're going to use Euler's formula and we're going to see how it's quite powerful. So if we actually rewrite z1 in terms of exponential form, this becomes e to the power of I times 2 pi over 3, right? And then z2 becomes e to the power of I times pi over 3. Yes? Well, what do we know about actually multiplying exponents? Their exponents add, right? And so that's all we need to do. So that means when we multiply z1 and z2, actually those angles, 2 pi over 3 and pi over 3, they're just going to add, which is what you should have discovered on the homework. So this is going to become e to the power of I times 2 pi over 3 plus pi over 3, because when we're multiplying these two powers of e, their exponents add. And so that is going to give us e to the power of I pi, which is negative 1. We're done. Easy, right?
So, in question 2a, it's written e 2I pi over 3. Is that equal to e to the I times 2 pi over 3?
Yes. That is what we call the commutative property of multiplication, which we learned in 7th grade, I think. Okay, we could also do division, right? Because division is just subtracting the exponents. So z1 divided by z2 is going to be e to the power of I times 2 pi over 3 minus pi over 3, which is going to give us e to the power of I times pi over 3, which you could calculate as cosine pi over 3 plus I sine pi over 3, which is 1/2 plus root 3 over 2i. Okay? Any questions? Well, actually, if we plot these on the complex plane, we see quite an interesting fact about what multiplication in complex numbers actually means. So allow me to do so. Suppose we were to first plot z1. Z1 is e to the power of I times 2 pi over 3, right? And so that corresponds to a radius of 1, because there's a constant of 1 in front, and an angle of 2 pi over 3. Right, so that means z1 is going to be right here. And this is going to form an angle of 2 pi over 3. That's z1. Okay. Now, where is z1, z2? z1, z2 is negative 1, or e to the I pi, right? So that's a point with the radius of 1 and an angle of pi, which is why we get to negative 1. So that's going to be right here. And this is z1, z2. And now where is z1 divided by z2? That is e to the I times pi over 3. And so that's going to be right here, because that forms an angle of pi over 3. And here we have z1 divided by z2. Okay, so what you actually notice is that when you multiply by z2, which has an angle of pi over 3, when you multiply, you're actually just rotating the point by pi over 3. So multiplication rotates you by pi over 3 in the counterclockwise direction, whereas division actually rotates you in the opposite clockwise direction. And so actually multiplication by e to the power of I theta actually corresponds to a rotation by theta. That's quite a pretty fact. Beautiful is what I think, huh? Multiplication by a complex number is actually rotation.
So can we just use this instead of the method?
What method?
The thing is, could we just know that it's rotation and then rotate it instead of doing the thing that you showed us?
Like this?
Yeah, instead of that, could we just
I mean, they mean the same thing, right? I'm rotating it because I'm adding pi over 3 to the angle. I'm just showing it graphically.
Oh, you're right.
And here I'm subtracting pi over 3, which is also a rotation. Yes?
How much is the negative being rotated again?
Pi over 3?
What is pi over 3?
Yep. Just in different directions depending on if you're multiplying or dividing.
I got slammed into my head in wrestling match.
Okay, so this only works with E, okay? E is about 2.718. So it has to be that number.
11. I lost that match. I got fourth place in that tournament.
Any questions? Please do question 3, and then we'll go on to DeMoivre's theorem. DeMoivre.
I'm 11 and 6 in the season now.
They were able to do question 3 with that, right?
Yes.
Well, I know what E is. I know what E is.
Like 66.
Well, it's the base, this is the base of the natural, you know this is the base of the natural world.
Yeah, like for football teams, like in the team.
I knew one.
Right, that's my sister's school. Yeah.
Guys, make sure to work hard, otherwise I'm not going to finish the lecture.
We're on period now? Oh, are we supposed to?
Yeah, but then we have to plot it.
Oh, wait, that's not -1. That's complicated. I mean, yes, it's a family. Wait, no, it is. I got it wrong.
Wait, Mr. Nasca, why is EI pi -1?
That's Euler's identity.
Oh.
Or you could also write it as, right, cosine pi plus I sine pi. And then cosine pi is -1 and sine pi is 0. Okay, all done? Question 3?
No, sir.
What?
In cases like this, where there's like a 5 in front of the I, do we write it like this?
That would be wrong because it's I times 5 pi over 6.
So would I write it like EI 5 pi over 6 plus
Mhm.
pi? Okay.
Yeah, I don't know.
That's right. Yes. Okay, what's the answer for Z1, Z2?
Wait, is this correct?
-1.
Wait, is this supposed to be, did I put the 3 in the exponent?
Nope, that's correct. Yeah, 3 is in the front.
Yeah, well then what the heck is this?
So here you're just doing it in reverse, right?
Isn't
so you're
it,
converting
isn't
from
it,
this.
wait, is this correct? Just take a look real quick. Is this right?
I mean, that's not what I'm looking for, right? I'm looking for a
I know, like,
trigonometric form.
but like, does this convert into
Yeah,
this?
it
Because like,
does.
I'm confused
It
by
does,
the,
yes,
that
it does,
notation.
yeah.
Wait, no, in context that we were talking about, like, I would take it.
That's not the right answer.
Okay, guys, let's continue. DeMoivre's theorem.
I'm not talking about that one. I'm not talking about that. Yeah, okay.
All right, I can confiscate this.
Bonus ringing! Busted! Busted!
Oh, you're gonna add one more.
Busted! Busted!
Wait, someone needs to
Busted!
Well, if it was yours, you can turn it on silent. Okay, let's talk about DeMoivre's theorem. So DeMoivre's theorem, guys, Ruhan. DeMoivre's theorem is actually just a special case of Euler's formula. And it tells us that cosine theta plus I sine theta, when we raise it to a power of n, this is just going to equal cosine of n theta plus I sine n theta. So it's kind of like the exponent actually distributes to the angle. Also a pretty formula. Okay. And so this is actually a special case of Euler's theorem, Euler's formula, and it was derived about 50 years before Euler. And so that's why Euler's actually just generalized this with his formula. And so this is very easy to show using Euler's formula, right? So cosine theta plus I sine theta, that's just e to the power of I theta, right? Correct? Yes, thank you. And so now we just use rules of exponents, right? See on the board? Exponents rules. I wrote that just for today. No, I shouldn't lie. I should not lie. I didn't write it. I apologize. Okay, so if we use rules of exponents, this becomes e to the power of I n theta. And we can write this as cosine n theta plus I sine n theta. Okay, so that's DeMoivre's theorem. Je m'appelle DeMoivre. Okay, so let's do an example. Shh, quiet, please. So suppose that we were trying to let's suppose that we were asked to calculate this. 1 plus I to the power of, let's do something obscene, like 24.
Thank you for explaining why this theorem works instead of just saying, just believe it.
Good.
Thank you for providing the proof.
I feel like you're making a comment about something else, but I'll ignore that.
DeMoivre's theorem.
Okay, good.
I'm saying thank you for like providing.
I appreciate it.
And not saying just believe it. I think it's wrong.
Yeah.
Like you do it most of the formulas. Remember that?
Yes. Okay.
We've seen the proof, we believe it now, but blessed are the ones who haven't seen the proof. Yes.
So let's. The first step is to convert whatever's inside the parentheses to trigonometric form. Okay. You guys know how to do that, so I won't show you. This is just root 2 times cosine pi over 4 plus I sine pi over 4. That was the homework, right? Wait, I forgot to show you the foolish way, right? The foolish way would have been to expand 24 copies of this.
Hello. This is what you're talking about, Leo.
Thank you.
The best way.
Right? That's one of your homework questions to do that. That was a joke. Nobody laughed. Okay? So the first step is always to convert to trigonometric form. And then, now you have to split it up, okay? Because DeMoivre's theorem only applies when you have nothing in front, when it's only cosine plus I sine. And so you'll need to split it up. So the root 2 comes to the outside, and you have root 2 to the power of 24. And then you have cosine pi over 4 plus I sine pi over 4 to the power of 24. And now you can apply DeMoivre's theorem on this, right? Because you have a cosine theta plus I sine to the power of something. And so that exponent can distribute to the angles. That allows you to multiply the angles by that factor. And so what you're going to get is 2 to the power of 12 times cosine of 6 pi plus I sine 6 pi. Because pi over 4 times 24 is 6 pi.
Why not 2 to the power of 23? Because wouldn't that get you...
I don't know what you're talking about.
Me neither.
If you took root 2 squared. Oh wait, hold on. Root 2.
Let me just continue.
Look at it, try to figure it out.
Oh.
Yes. Root 2 is the magnitude of 1 plus I. Right, that's the first step for trigonometric form. Okay, so 2 to the power of 12 is, we've memorized this, right? 4096.
No, it's not.
And then cosine 6 pi is 1, and sine 6 pi is 0. And so your answer is 4096. Hey, if you guys want to do CS, you have to memorize all the powers of 2 up to like 1,000,000.
how did you get cosine 6 pi?
What about 2 to the infinity?
Cosine 6 pi is 3 times 2 pi, so it's 1.
No, how'd you go from?
Oh, it's pi over 4 times 24, right? That's DeMoivre's theorem. So the 24 multiplies the angle.
Oh, that's neat. No, that's beautiful, Mr. Nye.
Yeah, that's what I'm saying. Okay? Or you guys could have done the foolish way, right? You would have gotten the same answer, but 10 years later. Okay, do question 4, please. Let's try to finish the lecture on time, because the last part is the hardest. So the first step, oh, there's a typo in 4b. Sorry, 2 is supposed to say 1. Okay, so 4b has a typo. It's supposed to say 1 minus root 3i.
Yeah, that's what I thought too.
Oh.
I was so confused. 2 pi squared 7.
Okay, first step, convert to trigonometric form, and then you can use DeMoivre's formula.
Yeah, but you need to throw.
DeMoivre.
It's 4.
Oh, no.
Okay, if you want full score in the classwork, I'm only requiring the front page today. This is a one-time thing.
Thank you so much.
Okay, now. Yeah, we never have that. Yeah. Oh, okay, wait, it's back. Is it gonna be,
No, yeah, no, it's right here.
square root? Is it gonna be square root?
This is, yeah.
Yes.
You should watch the lecture.
Wait, sorry. 7.5.
Since we're here.
Wait, what is it?
Nope.
I don't think so.
It needs to be an angle, right?
Yeah, but I
Which angle corresponds to root 2 over 2? And negative root 2 over 2.
wait, but isn't it like I take this and then divide it by whatever I got?
Yeah, so that gives you root 2 over 2. And then you need to figure out which cosines and sine
You think it
angles
got me root 2?
you divide by.
But you get from the last one.
It's converting to trigonometric form.
That's kind of low. Yeah. I don't get how to get the magnitude. What? Oh, is it? Okay, so would it already have it here if there was a magnitude?
No. I need to calculate the magnitude of the complex number inside. It's 1.
Oh, okay. Thanks. It is 1. It is 1. Wait,
Your answer is 1?
No, I'm sorry.
Yeah.
So that was my last answer before I realized that was a minus.
What's your answer?
I.
Yeah, that's correct.
And then this one's 2 power 6 and 64? 64. Alright, yeah, I definitely did that. I memorized half of them. Alright. And then everything else is correct?
Is it just pi over 4?
Okay.
It's nerve-wracking.
You had to change it back to you're on this new chart. You put up the new chart.
Are these steps right? Wait, so the final answer would be cosine 21 pi over 2 plus cosine 21 pi over 2. Yeah, if you need a calculator, cosine 21. Oh. Not pi over 1. It's 7 pi over 9.
So I would just, do I only multiply the numerator?
That's correct. It multiplies the
So it's not like to the power of 6 times.
Get your head back up and write it down.
Wait, upstairs.
No.
Guys, let me keep going. Let me keep going and talk about complex roots. Okay, guys, be quiet, please. Suppose you were given the question z squared equals 1, and you were asked how many solutions are there to this equation? Very good, 2 solutions. And what are they? -1 and 1. How about this one? Z to the 4th equals 1. How many solutions are there?
2, 1.
1.
0. 2, 3, 4.
4. Yeah, you knew that. Okay, the 4 solutions are -1, 1,
I.
-I, and I. Right? Can you guys confirm that -I to the power 4th is equal to 1? Right? Yeah. Because I to the 4th is equal to I squared, which is -1 squared, which is 1. So z to the 4th equals 1 has 4 solutions. -1, 1, -I, and I. All right, next one. How many solutions does z to the 8th equals 1 have?
8.
Yeah, it has 8 solutions.
Let's go.
Here are the 8 solutions. We have plus or minus 1, plus or minus I, so same as the previous one. But we're going to have 4 more solutions. And where are they going to come from? It's actually going to be this.
Complex roots.
Plus or minus root 2 over 2, plus or minus root 2 over 2i. And that's 4 solutions. I'll prove it to you, okay?
That makes no sense.
It doesn't at first. Okay, I'll show you. Let's take, for example, root 2 over 2 plus root 2 over 2i. If we squared this, what will we get? You can check. This is actually going to be 1/2 plus 1/2 plus 2 times 1/2 I, if you just did FOIL, plus 1/2 I squared, which would give you I. Okay? So if root 2 over 2 plus root, okay, this is actually the square root of I. Okay, if somebody asks you what's the square root of I, that's what we say. And so that means that root 2 over 2 plus root 2 over 2i to the power of 8 is going to be I to the 4th, which is -1 squared, which is 1. Okay, so the question is, how did I come up with that solution in my head? And we used Euler's formula again. It's all about Euler's formula. Yes.
Wait, stop.
Okay, so the general rule is anytime we have z to the power of n equal to literally anything, literally any number, 1, 2, 3, 4, I, negative I, this will always have n solutions whenever you have a power of z to the n equal to something, equal to a constant. And the question we're trying to address is how we find those n solutions. Still same. Z cubed has 3 solutions. Z to the 5th has 5 solutions. Okay, let's talk about how we find them.
Wait, go back up.
Okay. Hurry. Okay.
Wait. Oh! Why do you keep doing that?
I'm sorry.
Just give me like a couple more minutes. Give me a couple more minutes.
Okay.
Please.
Let's look at some examples. Let's look at the case of z to the 4th equals 1. And let's try to plot all of the solutions, okay? So z to the 4th equals 1 has 4 solutions. Guys, be quiet. Z to the 4th equals 1 has 4 solutions, and where are they on the plot? We have positive 1, we have positive I, and we have negative 1, and we have negative I. Do we see a pattern? They form a circle. Okay, let me show you the 8 solutions for z to the power of 8. For z to the 8 equals 1, there are 8 solutions. We have 1, I, negative 1, and negative I. And we also have root 2 over 2 plus root 2 over 2i, whatever this is, this, and this. Okay? That's quite interesting, right? Very interesting, yeah.
As you go up in powers, would it look closer to the circle?
Yep, they're just evenly spaced points around the circle.
So z to the 109 equals 1 has 109 solutions?
Yes.
This is what I actually said. Oh, that's beautiful.
Yes. It's called the fundamental theorem of algebra, right?
That's the fundamental theory.
Fundamental theorem of algebra.
Yeah, exactly.
Any polynomial with degree n has n complex roots.
It's fundamental. Why did we learn it earlier?
I don't know.
It's fundamental doesn't mean easy, right? Fundamental means fundamental, foundational.
It means if you're going to have fun while you're doing it, you're inventing it.
Anyways, let me explain how we actually solve questions like this. Okay? So suppose we were given a question, z to the n equals r times e to the power of I theta. Ruhan, you're the loudest person there, so that's why I keep calling your name. Okay, it's annoying. Shh, please let me finish and you will understand it. If you don't listen, you don't learn it, right? Okay? So suppose we're given an equation, z to the n equals r times e to the power of I theta, right? Any number, any complex number can be written as r times e to the I theta. So that's why I've written it like that. So for example, on your classwork, you have I, you have 1, you have 16. All of them can be written in this format. And if we have the number in this format, the n solutions for z can be represented in this form. It's somewhat large, so bear with me. Z equals r to the power of 1 over n, right? That's just a square root, or not a square root, but a root n. So that makes sense so far, right? A power of 1 over n times e to the power of I times theta over n plus 2 pi k over n, where k is some integer 0, 1 to n minus 1. And so k gives us our n solutions when we iterate between 0, 1, 2, all the way to n minus 1. That gives us our n solutions. It's very similar to how when we were solving sine and cosine equations, how we had a plus 2 pi n. It's the same exact concept. Okay, we have to iterate in order to get all n solutions. Right? And you can confirm by reversing this equation, right? If you reverse this and you exponentiated both sides to a power of n, you would get r times e to the I theta over n plus 2 pi k over n times n, right? So the 1 over n disappears because I've raised it to a power of n. And then I've multiplied the exponent by n because I've raised it to a power of n, right? And so this simplifies to, I should keep using red. This simplifies to r times e to the power of I, and then the n distributes to both terms, right? And so that leaves us with I times theta plus 2 pi k. Right? And 2 pi k, that gives us the same exact number because we're just rotating the angle by a 2 pi, right? Yeah? So if we had, right, if here is e to the I theta, multiplying by, or changing the angle by 2 pi k, that's just a 2 pi k revolution. Yeah, and it gives us the same point, which is why we get the same exact number for z to the power of n. And that's why z has n solutions, because it can go around that many times.
Oh, that's beautiful.
And if we go over n, so if k begins to exceed n, then we start to get the same numbers for z. Sure, yeah, sort of.
Yeah, I'm confused.
So which of these do we have to know?
You have to memorize this.
Of course, it's that one.
This is the one that must be memorized.
You have to memorize it.
I don't have it memorized, but I would know how to derive it, so I don't need to memorize it.
Yeah.
I don't need to memorize it. I can derive it every time I need it.
Teach us to derive it.
I just taught you how to derive it. Oh my gosh. What is this? Right? Okay, guys, really the only thing you really need to memorize is the 2 pi k over n, right? That's the only thing, because this makes sense, right? R to the about 1 over n, that makes sense. And then theta over n, that makes sense. You're just dividing the angle by theta once you find it. And so really the only thing to remember is plus 2 pi k over n. Okay, so to go back to the diagrams with all the points on the circle, right? All you're trying to do is find one value, so one possible solution of z, and then all you need to do is just increment it by an angle of 2 pi over k, 2 pi k over n. Right? So if we had, one solution here, right? We just need to find all the other points on the circle by changing the angle by 2 pi over n. Right? Every single increment is 2 pi over n. Just saying, this explanation is a lot better than whatever I told 1A, so,
Oh, so n's the increments?
K is the increment, and n is the number of increments. Let me give you guys an example. I realize that may be helpful.
Oh, I sort of get it.
Okay? All right, I'm going to go to the next slide. Okay, is that okay? All right, let's suppose that we have the equation z cubed equals 8, right? So this is my example. This is quite similar to none of them, but okay. So how many solutions does this have? This has 3 solutions. One of them we know, it's 2, but what would the other ones be? That's the question to find out, right? So first, guys, the first step is to write the, the number in terms of the exponential form. So I would start like this. So z cubed equals 8 times e to the power of I times 0, right? Because e to the power of I 0 is just 1. And so 8 can be written in that format. Okay, and then we can apply the equation that we all have written down. Okay. Because it's on the positive real axis, so it has an angle of 0. 8 is just 8 plus 0I, right?
Wait, if it weren't on the positive consensus, would it be like 180?
No, I mean, if you graph it, right? 8 is here. That has an angle of 0. Yeah. Okay, so we first write the constant in terms of exponential form, and then we use our formula. And so z equals h to the power of 1/3 to the power of, a to the power of 1/3 times e to the power of I times 0 divided by 3, which is just 0, 0 plus 2 pi k over n, which is 3, right? Yes? And so this is true for k equals 0, 1, and 2. So we have 3 solutions. And so the task is simply to find each one and express them in terms of standard form. So h to the power of 1/3 is 2. And so we have 2 times e to the power of, let's do k equals 0 first. If k is 0, then our angle is 0. So that's one solution. Our second solution is when k equals 1. And so that's going to be e to the power of I times 0 plus 2 pi over 3. And then our third solution is 2 times e to the power of I times 0 plus 2 pi over 3 times 2, when k equals 2, right? So our third angle is 4 pi over 3. Okay? And so if we were to graph these 3 solutions, here's what we would get. This would be our first one, that's 2. And our second one is at angle 2 pi over 3, right? So that's here. This is still 2. And then our third solution is, then our third solution is 4 pi over 3, which is right here. Okay, so that's how we get our 3 complex roots. And they'll always form a spaced out circle depending on how many solutions there are.
And this is a trigonal planar shape.
If you're taking chemistry, I don't remember all those, what are they called? IUPAC?
No, it's like
Molecular.
Vesper. Yeah. People found that very hard to memorize, but I don't know. Anyways. Okay. So as a final step, you guys would also have to convert these to standard form. So the answers are 2 and what is this? -1 plus root 3i and -1 minus root 3i. And these are the 3 complex roots for z cubed equals 8. This is a very beautiful section of math, and you should appreciate it.